So a very good evening to you all. So today we will start the basics of geoprocessing using Python. So till now we have studied basic syntax of Python programming language. Then in the second lecture we introduced I gave introduction to the basic libraries NumPy and Matplotlib. NumPy is for numerical computations and Matplotlib we used for visualization. So today with the help of these two libraries, we will see that how can we read and write a raster data. So for this, we will be using a library called GDAL. So for first I will give you a basic introduction about raster data. Anyway, in the first lecture, these all things were covered in detail. So just for the sake of completion, I will just go through like what is raster data, and then we will proceed with how to read the raster data using Python. So what is raster data? Actually, raster data represents some objects or variables on the Earth's surface as a matrix of values. So the matrix of values in the form of pixels, cells, or grids. So the raster image may be representing surface reflectance, or even it can be temperature as well. So any feature on the Earth's surface that is represented using, so all the continuous features can be represented using a matrix of values, maybe two-dimensional or three-dimensional. So actually an raster image can have multiple layers, single layer or multiple layers. So each layer may be called a band also. So a raster is an image with matrix of values representing the values of some observed attribute. So every cell will be representing some observed attribute. So that attribute may be the surface reflectance, or it might represent some temperature, or even it could be elevation of that point on the Earth's surface. So bands, so it will be represented like a cell or grid of cell of values or grid of values. So every grid will represent some measured or observed attribute. So this attribute could be anything. So similar, then there can be multiple bands or layers in a raster. So bands of a raster correspond to different variables. So these may be like temporal values. So like one layer may represent temperature at certain point of time. Then second layer may represent at time t+1. Third may be time t+2. Or these can be reflectances in different EM wavelengths. So for example, here we can see that this first layer shows the spatial variability of temperature, and the second layer may be the same spatial variability but at different time. So this a band in an image can represent a temporal phenomena, or it could be some in different electromagnetic wavelengths. So an image will be represented like this. So if we see, like suppose if we have an image like this, and if we zoom on, then we will see it like this. But ultimately in the memory, it will be represented using a cell of a grid of numbers. So every pixel, every grid will be representing the intensity or pixel value. So raster bands. So some rasters have single band, some rasters may be single band, while some others may have multiple bands. So basically a band is represented by a single matrix of cell values, and raster with multiple bands contain multiple spatially coincident matrix of cell values representing the same spatial area. So for example, a single raster data set is like, suppose if you take a digital elevation model, so that is a single single raster band. So each cell in the DEM contains only one value, so representing elevation of that particular point. So single raster bands can be it could be a binary image. So binary image means all the pixels values will be either 0 or 1. Or a single raster band can be represented using a grayscale image also. In grayscale image, there will be different levels of different intensity levels, grayscale levels will be there. Maybe suppose if the image is represented using 8-bit value, then the intensity levels will be from 0 to 255. Or if the intensity is represented as 16-bit, then the range will be different. Or the single band raster can be displayed using a color map also. Suppose if you have a classified image, in that there are some certain discrete values only. For example, 1, 2, 3, 4, or 5. So what we can do, this single band raster can be represented as a color image also. Like all the ones can be represented using a color, like here you can see that yellow, or twos are represented using a different color, and threes are represented as a different color. So a single band raster can be displayed as a binary image, grayscale image, or using a color map, it can be displayed as a color image as well. So multi-band raster now, an image can have multiple bands also. Like for example, a satellite image, for example, has multiple bands representing different wavelengths from the ultraviolet through visible and infrared portions of the electromagnetic spectrum. So if you see a multi-band raster image, you can see that these are the pixel intensities at red band. So because if we see as a single band, so it will be shown as a grayscale image. So similar way, green band also will have some pixel intensities. Similar way, then blue. Then when we combine all these three bands together, then we get a true color or RGB composite image. So this, when we overlap all three bands together, then we get a colored image. So like here you can see that when we combine all three RGB data sets, then we get a RGB composite or true color image. So here you can see a natural color image of Haridwar area. This image has been acquired using LIST 3 satellite onboard resource set 2A2 satellite of ISRO. So this was the basic introduction to raster. So a raster image is a cell or a matrix of matrix of values. And raster image can have a single band or multiple bands. So now we'll be using a library called GDAL for reading and writing raster images. Actually, raster images can be. So first, what is GDAL? So GDAL stands for Geospatial Data Abstraction Library. So this is a computer software library for reading and writing raster and vector geospatial data. So GDAL supports a variety of formats. Actually, raster and vector data can be stored in different formats. So GDAL can be used for, GDAL supports almost all of the vector and raster data formats for both reading as well as writing. So why should we use GDAL? So actually, first and foremost is GDAL is free and open source. Plus, GDAL supports over 80 plus image formats and map projections. So GDAL, actually with the help of GDAL, you can read almost all the vector and raster formats available. Plus, it supports almost all map projections as well. Plus, GDAL has interface for command line. Plus, it has bindings for C, C++, Python, R, and Java also. So basically, GDAL is written in C, C++, but it has bindings for all other programming languages also, Python, R, Java, etc. Plus, GDAL is used extensively by world's large geospatial data services. Actually, all world's most geospatial data services, maybe even Google Earth also, you can take that, they are also using GDAL. Plus, it has extensive test suite and active developer community also. So there is a lot of documentation also available, and you will get a lot of tutorials on net for this. Plus, GDAL also includes extensive support for vector data sets. So GDAL can be used for vector as well as raster data set. So actually, there are a lot of proprietary softwares also are using GDAL library. So we will start with GDAL raster data model. So GDAL raster data model means how the raster data is represented in GDAL. So if the Actually, actual image can be represented or saved in any of the format. Maybe it may be net CDF or GeoTIFF, big GeoTIFF, or HDF format, HDF or IMG format. But ultimately, when you read the image using GDAL, so GDAL, the actual data will be represented in a raster data model. So when you read an image, so the GDAL will return you a data set. So it will return you a data set object. So data set object in turn will have, if it can have multiple bands. If it is a single band image, it will have a single band. But if it has more than one band, then data set will contain multiple bands plus a geo transformation information available to that image. So with the help of geo transformation information, those pixel number and line numbers will be converted to actual real world coordinates in terms of latitude or longitude, so that the image can be projected or displayed on a map. So data set will contain multiple bands plus geo transformation information for projecting or displaying the image on a map. Plus a band will have the data associated with that band, because every band will have a matrix of values. So in band, in turn, you will get some data array and it might have some overview bands at coarser resolution. So that suppose if your image resolution is very high, and suppose if you are looking at a entire image, if your image is very high, if your image has resolution of your image is very high, and if you are looking the image at entirely, so drawing that image on your screen will take a lot of resources and time. So for saving it, what happens, the same image is represented at different coarser resolutions, so that the rendering on the screen will be faster. So there will be multiple overview bands at different spatial resolution, maybe half the pixel size, double or 1/4, 1/8, and so on. So there can be multiple overview bands also associated with that image for faster rendering on web browser or some softwares. Next thing, like what is map projection? So a map projection is a way to flatten a Earth surface into a plane. So map projection is a way to project a three-dimensional surface to a two-dimensional plane to make a map. So this requires a systematic transformation of the latitude and longitudes of locations from the surface of globe into the locations on a plane. So all projections of a sphere on a plane necessarily distort surfaces in some or other way. So actually these are different map projections. It can be geographic or web Mercator, golf meters, this is equal area projection, or azimuthal equidistant. So every projection will distort your 3D surface in some or other way, because whenever you are projecting a 3D surface into a two-dimensional surface, some sort of distortion will be there. So coordinate system. So there are numerous conventions used globally for representing the coordinate system for a map data. So whenever you are projecting a 3D surface to a 2D or into a map, so you need projection system plus the coordinate system. So the coordinate systems can be represented in multiple ways. So there are like one way is PROJ4. So this also can be used to represent coordinate system, or OGC WKT, OGC well-known text, or OGC WKB well-known binary, or coordinate system can be represented using EPSG codes, or even some XML formats also are there for defining a coordinate system. So generally, if you see in an image, the coordinate of an image on the is like it is divided in pixel number. Any pixel is referred using its pixel number and line number. So the topmost left corner will have the coordinate 0, 0, and all the columns will be called pixels and rows are called lines. So pixels will be incrementing from left to right, and the lines will be incrementing from top to bottom. So top 0, 0. So top left corner will be 0, 0. So similarly, suppose there are n pixels. So the top right will be the coordinate of the top right pixel will be number of pixels into 0. So this direction we will call pixels and this direction we will call lines. So similar with this corner will have coordinate 0 and number of lines, and this last or bottom right will have coordinates of number of pixels and number of lines. Now, how do we convert pixel any pixel which is in the image coordinate system to real coordinate system? So in image coordinate system, any pixel will be indexed using pixel number and line number. Now, how do we convert this pixel number and line number to its real world coordinate or latitude and longitude? So with every image, as I said, the affine transformation information of the image will be stored. So affine transformation information is a 6-element image. So the 0th element of that will be origin x coordinate. So first element will represent pixel width. Second coordinate will represent pixel rotation. So if in your image north is pointing to upwards, then this rotation will be 0 degree. And third element will represent our origin of the y coordinate. Fourth represents y pixel rotation. So in same case, if the north is up in your image, then this fourth element will be 0. Then fifth is your pixel height. So this will be a negative number. So now here you can see that suppose this was our original image, and the geotransformation information of this image is like this is x0, y0. So 0 origin x coordinate is x0 and 0th element, and origin y coordinate, the third element is y0, and the pixel resolution in x direction is px and pixel resolution is y direction is py. Plus suppose if we are assuming that the north is up. So suppose if you have to calculate the real world coordinate of this particular pixel, so this can be calculated using, like you know that this is 0 0. So this pixel is pixel number 4 and this is line number 3. So this pixel is pixel number 4. You can see the 1 2 3 4 fourth pixel and 0 1 2 3 third line. So the real world coordinates of this can be calculated using x0. This is the coordinate of 0th pixel. So x0 plus 4 into px. So because we are 4 pixels away, and y coordinate can be calculated using y0 minus 3py, because y direction the resolution will be in the negative. So y0 minus 3py. So this way we can calculate the real world coordinate of any pixel from image coordinate to real world coordinate using the geo transformation information available with the image. So for this demonstration, I will be using for this image, for this today's demonstration, I will be using this image for reading and writing. So this is a false color composite of Haridwar area. So this image was acquired somewhere in October 2019. So this image is acquired by list 3 payload of the resource at 2A satellite. So this particular image we will be using for demonstration today. So this is a multi-band image. So let us see how to read this particular image. This is available in GeoTIFF format. So anyway, if JIDA supports multiple formats, you can read any other format as well. So let us start. So first thing what I am doing, I am just importing OS package. Actually, OS package with the OS gives our interface to the operating system. So my data is this particular image is stored in this some particular directory. So what I am doing, I am just changing my working directory to this directory where the data is stored. So with os.chdir, os.change directory, I'm just changing my working directory to this folder. Then in JIDAL, there is actually JIDAL provides, as I explained, JIDAL provides command line interface, plus it has APIs in Python as well. So first we will start with a command line interface. So in Jupyter Notebook, suppose if you want to run any command that is available on your system, so that you can run using, so just you can with exclamatory mark, any command, any line starting with the exclamatory mark is a shell command or command to be interpreted by your shell. So here actually our Windows shell, it is there. So suppose if you have to run any system command, so you just need to just start the line with exclamatory mark. So actually before that, first thing you need to install JIDAL to your system. For installing JIDAL, either then you can just install it using command prompt using conda install JIDAL, or from your Anaconda navigator as well. Also you can start install. So once JIDAL is installed, for installing the command is you can use conda install JIDAL, or through pip also you can install. If you just run this command conda install JIDAL, so JIDAL gets installed on your system, or otherwise you can just start your Anaconda navigator, activate your environment, and then there search packages, and packages not installed, then it will list JIDAL. So from there also you can select JIDAL and install. So once JIDAL is installed, so first command is JIDAL info. So anyway, this line is starting with exclamatory mark. So it means that this is a system command. So JIDAL info. So JIDAL info extract the information about any image. So JIDAL info. Then I am passing it switch with nomad. Nomad means I don't want metadata. I don't want to print metadata associated with the image. And then third argument, I am passing it the image for which I want to get the information. So if I run this command JIDAL info, so it returns the information. Here you can see that it says that driver. So the driver used for opening file is gtif or geotif driver. Then the name of the file. The name of the file is haridwar.tif anyway. Plus it has stored a overview band also with this image jidal.tif.ovr. This might have been created by this GIS software what we used. So OVR contains cursor resolution, same image but at the cursor resolution for faster rendering on your screen. Plus it has an associated XML file also. Then the size of this image is 1151 by 1151. So there are 1151 rows and 1151 columns in our image. So the width of our image is 1151 pixels. Similarly, the height also is 1151 pixels. So this is a square image. The coordinate system. So the coordinate system is GeoGCS. So geographic coordinate system is being used with this image. So the datum is WGS 1984 and so on. So similarly, now you can see that these are the transformation information. So it says the origin pixels. So the origin. So the X0 and Y0, whatever I explained in the explained about geo-affine transformation. So this is the origin. So origin 00 pixel has coordinate 77.99 and 30.00. So X is our longitude and Y is latitude. So pixel size. So in X direction, the resolution is 0.0002 degree, and similarly in Y direction minus 0.0002 degrees. Then it has calculated the coordinates of the corners. So these are the coordinates of upper left corner, lower left, upper right, lower right, or center. Plus now it says that there are 4 bands in this particular image. So band 1 data type is unsigned 16-bit integer. So band 1 pixel intensities are stored in the form of 16-bit unsigned integers. And the mean pixel intensity is 138.229 and standard deviation is this. And plus there are so many overview bands at these size. So original size is 1151 and the first overview is at half of the pixel or double pixel size or half resolution. Then one overview is again 1/4 and 1/8. So similarly there are other bands, red, green, blue, and for last band it says that there are 3 bands only. This is a 3-band image. First band is red, second green, and third band is blue. So with JDAL info, you can extract information about any image. Now let us see the same. Now I will try to extract the same information using JDAL's Python bindings, so that because you will not be using all the time the command. So whenever you are writing scripts or some program, so in the when you are writing a program, there you need to use Python APIs only. So for using Python APIs, actually whatever code I will be showing here, this is just for the simplicity. So this code may not be useful for production environment, because there same code can be written in multiple ways. So this may not be most efficient way to write the code, but just for the simplicity, I have written it. So this you should not use it for the production environment. This is just for demonstration only. So first thing for using JDAL is, first thing what we need to the name of the package is OSGeo. So first thing, from OSGeo we need to import JDAL. So this should be the first statement, first import statement in your code. So from OSGeo import JDAL. Then second, I am importing matplotlib, pyplot as explained yesterday. Then numpy. Then parslib. Actually these may not be required. OS anyway we have changed the library. Then OSR is for special reference. I will be talking about it later. Then a math library. So basically important thing is OSGeo. From OSGeo import JDAL. So once these statements are imported, so just I am changing my working directory. I am calling it base directory where my data is stored, D drive, and RMS, Haridwar, and multi. So I'm now anyway, it is already done, but I am just changing my working directory to this. So in this, as I explained, the name of my file is haridwar.tif. So I am creating a variable called file name. So in that I am storing the value haridwar.tif. Now for opening this file, I need to call the function JDAL.open. Actually Python, it is case sensitive, so your O must be capital. So JDAL.open, and you need to pass it an argument called name of your file. So here the name, I have stored my file name in the variable file name, so I am passing it the variable file name. So JDAL.open file name. So if I see after this executing this statement, if it prints something like this, a string object, so it means that your file has been read successfully. So you can include if else also, if it returns nothing, then there is some error in. Actually, I have not introduced, I have not included any error handling in this, but you can include in your code error handling as well. So here after the file, if the file is read successfully, it returns you something like this, OSGeo JDAL dataset. So it has returned a dataset. As I explained, JDAL's raster data model, data is represented as a dataset. So it returns DS. So suppose if I change the name to something else, that non-existing file, it will not return anything. So now it has returned none. So because it means it was not able to read the file. Now the first statement, what it printed, our JDAL info, it printed the names of file, which all files are associated with this file. So same information can be extracted using. So here I am print file ds.getFileList. So ds.getFileList will return you all the files which are associated with this data set. So here you can see that there are 3 files associated with this data set: haridwar.tif, overview, and XML. So same information we got here. So next, suppose if you want to calculate the width and height of your image, like how many pixels are there in X direction and how many pixels are there in Y direction. So same thing, like you can call ds.rasterXsize. So ds.rasterXsize will return your pixel width in pixels in X direction, or width of your image. So it says 1151. Similarly, suppose if you have to calculate height of your image, so ds.rasterYsize, it returns the pixel height, image height. So now next, suppose if you want to extract the projection information. So the function you need to call your dataset dot get projection. So dataset dot get projection returns the projection associated with your image. So it says the your coordinate system with your image is geographic coordinate system, GeoGCS with WGS 84 datum, and units are in degrees and so on. Now once projection information got, now suppose if you want to extract the geo transformation or affine transformation information available with your image. So with the help of what do you do? What do you do with affine transformation, geo transform? With the help of geo transformation information, the image is projected onto a map. So if you can, so for getting the geo transformation, ds.getGeoTransform returns the transformation information. So here you can see that it has returned a 6-element tuple. So as explained, the first element of our transformer, this is the 6-element tuple. So first element is the origin coordinate x0 x0. Then first coordinate is pixel resolution in x direction. Then third shows the rotation. If it is 0 means north is up in your image. Then this is y0. 0 pixels real world coordinate. Then this is rotation in y direction. So if this is also 0 means the north is also up. There is no rotation in our image. Then this last number represents our resolution in y direction. Similar ways, like suppose if you want to extract origin or pixel size, then 0th element and 3rd element represent our origin, longitude and latitude, and pixel size are 1st and 5th element. So this 0 and 3rd element, these are the origin coordinates. Then GT1 and GT5 are pixel coordinates. So similar way, suppose if you want to calculate the coordinates of your corners, so either you can just simply multiply your x0 plus your pixel number and line number and multiply by their resolution. Or there is a convenient function also available in GDAL that is called GDAL.applyGeoTransform. So for GDAL apply geotransform converts your pixel number and line number to its real world coordinate using. So with the help of this transformation information, it converts your pixel number and line number into your latitude and longitude. So actually, if you take our upper left corner, so upper left corners coordinates in image coordinate system are 0, 0. Upper left will be 0, 0. So now, suppose if you want to convert its, want to get its latitude and longitude, you need to just call GDAL.applyGeoTransform and pass it the geotransformation and pixel number and line number. Similar way for upper right corner. Upper right corner will have in image coordinate system, it is our width of our image. So in x and y is 0, 0 only. Then lower left corner is 0, y height of our image. Then lower right corner is width, height of our image. Then similar way you can calculate the coordinates of your center pixel also, like raster x size and raster y size by 2. If you divide by half, you get. So this way you can calculate the coordinates of any pixel. Now suppose there may be some metadata also associated with the with your image. So metadata, the producer of the image might have stored some metadata. Suppose if you want to extract the metadata, you can just call ds.getMetadata function. So ds.getMetadata function prints some metadata. So suppose here it says some access constraint, so it is available only to restricted users, whether this represents area or point. So it represents some area, then city, Hyderabad, contact addresses of the producer of the data, and so on. So actually there is another function in Python available that is called pprint or petty printing. So this information is not quite readable. So suppose if you want to make it readable, you can just call the pprint. So preprint stands for petty printing. So pprint.preprint if you do, so the same information is represented in more readable way. So it says whether this is an area or point. So actually this is a metadata associated with image. So if GDAL, this metadata is showing area or point, So what does it mean? It is representing an area. So it is area, it means the coordinates, whatever you are seeing here. So these are the coordinates of left corner of your pixel. So this is by default in JIDAL. Suppose this area or point is representing point. So this means when the coordinates you are referring to are the coordinates of the center of your pixel. So this area or point is means area means the coordinates what you are seeing here are the coordinates of the leftmost corner of your pixel. So when it is area or point will be point, it means the coordinates are the coordinates of center of your pixel. Similarly, these are the data, other metadata like city. This data was produced in Hyderabad, contact email, and like there you can see that file format is GeoTIFF, date of pass. This image was acquired on 21st February 2018. Data prepared by NRSC, National Remote Sensing Center, and so on. So sensor list three sensor and resource set to spacecraft. There are 3 bands in this image, name of the data set, and so on. So this is the metadata associated with this image given by the producer of this image. Similar way, you can get some, suppose if you want to extract the image structure, so you can just get ds.get metadata image structure. So it says that it is interleaved pixel by pixel. Now suppose if you want to extract how many bands are available in your image, you can just call ds.raster count. It represents the number of bands available with your image. Similar way, now suppose you want to extract data for individual band, and like here this it was showing some statistics about that every band. So there's that information also you can calculate. Now let us see. So here what I have done here. So actually this is a multi-band image. So this I have started a loop. So for I in range 1 to, so actually in JIDAL, the generally in computer science indexes start with 0, but in JIDAL the band numbers doesn't start with 0. So band 1 will start with number 1 only. So here I am starting a loop with for I in range 1 to number of bands in my image plus 1. So suppose in my image there are 3 bands, so I am starting a loop from 1 up to 4. Range 1 to 4. 1 to 4 means it will return me numbers 1, 2, and 3. First I am starting a loop. So first thing you need to get from your data set, get raster band. So get raster band will fetch the, if you remember about raster data model. So once you read an image, it returns you a data set. So data set will have multiple bands. So now for extracting, and in every band will have data plus some overview bands. Plus it can have some metadata as well. So first thing is what from the data set we need to fetch individual band. So fetching an individual band, what is the function available? So your data set dot get raster band, and you need to pass it the argument band number, which band number you want to fetch. So first I am fetching band number, like when i's value will be 1. So band equal to I will be fetching band 1. So like suppose what interpretation of this band has been given. So then band dot get color interpretation will give you the interpretation of this band. Then anyway this will return as a number. So now this number you have to map to some string. For that there is a function in JIDAL dot get color interpretation name. This will convert this integer to a string. Once this is got, then we can get like block size of your image, and a similar way you can calculate like how many overviews are available with this in this particular band. So if there are multiple overviews, then we are iterating over those overviews one by one. So now if I run it, you can see that band 1 has block size of 1151 into 1, and its color interpretation is red. So overview, so there are three overview bands, or 3 overview bands. One is of this size 57 by 576. This is just half, then 1/4 and 1/8. Similarly, other second band is had color interpretation green, red, and so on. So once this is done, then you can delete. Actually, for freeing these resources, you can just delete our data set. Now suppose similarly, now suppose if you want to get the statistics, so in GDAL info you can pass GDAL as minus stats. Just if you want statistics about your image, GDAL info minus stats. Then I will pass nomad also. Basically, if I do not pass no metadata, it is no MD. It is uh, printing the metadata also. No MD. So here now, just basic information like this band 1 is it has a block size of 1151 cross 1. And minimum value is 45, maximum value is 315, mean value is the standard deviation. So this is representing some statistics about every band as well. Now suppose same thing if you want to get it from the Python, you can just first thing like you need to just open GDAL open. GDAL.open your file name. Then anyway we are iterating over all bands one by one. So fetching first band, then band.compute statistics. Band.compute statistics. Actually, if you pass it the value false. So if you pass it the value false means then the statistics are calculated on the original image. Suppose if you pass it compute statistics and where the value argument is true, then the statistics will be computed on the overview band. So now we want to calculate it on the original image. So we are passing the argument as false. So band.compute statistics returns your minimum, maximum, mean, and standard deviation of that particular band. So we are fetching band, calculating statistics for that band, and iterating over to the next band. So this way you can calculate. So now these both are matching 45 and 315. Mean is 138.299. Standard deviation is 4213, 4213, 72, and 7. So this way band.compute statistics, you can get the statistics about all your bands. Now we have seen basic statistics. Now let us see the data. So you see, as I explained, ultimately the image is represented using a matrix or cell values or matrix or grid values. So now let us see that how does that matrix look like. So first thing what we need to, suppose we want to fetch the band 1. Anyway, our data set still is open. So ds.get raster band. So ds.get raster band. It is band 1 from our data set. So now we have fetched the band. So if you remember the data model, so every band will have data plus some overview band also. Now we are interested just only in the data. So for fetching the data, what you can call on band.read as array. So band.read as array will return you the data or two-dimensional matrix for that band. So this will ultimately return you a two-dimensional NumPy array. So band.read as array will return data. Now suppose if I print this data, here you can see that this has returned us a two-dimensional matrix. So if you remember this, I have shown that ultimately an image is represented like these cell values or grid of grid. So same thing now if I fetch the band 1, it returns me actually for the efficiency reason, NumPy doesn't print all values completely, so it just prints you an overview. So similar way you can fetch any other band also. Suppose if I am interested in band 2 pixel intensity, I can change it to band 2. You see now the values have changed a bit. So once this is done, now let us visualize this. So for visualization, ultimately like yesterday we saw, so matplotlib.imshow. Imshow is for
showing a two-dimensional matrix. So if you have one-dimensional array, then you have to use matplotlib pyplot.plot. But in case of two-dimensional array, you need to call IMShow. So here first I am creating a figure of size 10 by 10, and same thing I am calling plt.imshow. I am passing is this argument as this data whatever I got, and in the color map I am passing it as gray color map. So here you can see this matrix is represented like this. So this is the single band. We have extracted only a single band. So this was our original image. So this was our three-band composite image, and now same image we have read using Python, and but we are displaying just a single band. So red band, these are the pixel intensities in red band. Now suppose if you want to attach a color bar to this, plt dot color bar, show you the color bar as well. So here, so this is the map of pixel intensities. Similar way, you can change the color map to any other color like we showed yesterday. Now this way you can visualize the image, read the image, extract the band of your interest and visualize it. Now suppose if you want to increase the size of your image, now suppose you want to view all the bands together, red, green and blue all together. So here again I have created a figure of size 30 by 3. Then what I am doing, I am iterating over all the bands one by one. For I in range 1 to ds.raster count. ds.raster count returns me the number of bands in my image plus 1 I have to do because band number starts with 1. So 1, 2 and 3. Then I am fetching that particular band. Then I am creating a subplot, plt.subplot. I am creating one row and three columns. One row in three columns and band number. This is like a plot number I. In plot number I am just plotting this band dot read as array. So I'm calling on that band dot read as array. So here all the three bands are. So you can see that these all are grayscale images, but these are pixel intensities in different electromagnetic wavelengths. This is in red, green, and blue. So slight difference, you will see that these features are not quite visible in this and these bands. So this way you can read and multi-band raster using Python and visualize it using matplotlib. So once this is done, you can just close it. Now anyway, now this we have just visualized images band by band. Now let us see how do we visualize a composite or colored image, multi-band image. So anyway, our DS is still open. We have not closed the DS. So if I directly, suppose if I, instead of fetching bands one by one, I want to fetch all bands together. So I'm just interested in the data on the all bands. So what I can do, if I directly call on my data set, this is my data set, open DS. So if I call ds.read as array, so ds.read as array without fetching any band. So if I just call ds.read as array, it returns me all three bands together in the form of a three-dimensional array. So if I call multi-data, if I see the shape of this multi-data, it says 1151 by 1151. So it returned me three matrices of size 1151 by 1151. Right. So actually for displaying it in using matplotlib, first I need to stack these all together. Actually, I just need to reshape it and bring it to this format. This is just for reshaping so that it can be plotted using matplotlib. Actually, matplotlib plots the data, if Matplotlib based plots multi-band image, if and only if your data is in m cross n and number of channels or number of bands, if they come in last. So for that, what I have done, I have just reshaped my data from 3 into 1151 cross 1151 into 1151 cross 1151 cross 3. Just I have reshaped this data. Then just if I call plt.im show this reshaped data. So now you can see that this way we can visualize. Now you can see that these are our two images. So this way we can visualize any multi-band raster as well. Once this is done, then finally you can close it. So, so this is just an overview. Like I will just recap of what we have learned. So basically, once you read an image, so image could be in any format. So independent of the format used for storing the data, your GDAL will return your data set. So data cell in turn will have bands plus geotransform, and band in turn will have the data array and can have some overview bands also with this. Plus data set will have some metadata as well. So for opening an image, you need to call GDAL.open and pass it the name of file which you want to read. Then once data set is read, then you can fetch individual bands from your image, like your data set dot get raster band and pass it the number of band which you want to fetch. Then once band is retrieved, then from the band you can get metadata, overview bands or data. Suppose for retrieving the data for your band, you need to call band.read as array method. Or suppose if you are interested directly in reading all the bands together, so that directly once you open your data set, and from your data set you call read as array function. So read as array will directly read you all three or whatever bands are available in your image all together. And for converting pixel image coordinates for converting coordinates from image coordinate system to our real world coordinates, you need to call apply geotransformation function. So this was all. Now next, suppose if you want to so now suppose if your image size is very large and you have limited memory available at your system, so that what you can do, for efficiency reasons, you can read your data set partially or block by block, or suppose you are interested only in certain portion of image. So why to waste entire why to take more waste resources? So suppose if you are interested in only reading partial data set, not the entire data set altogether. So there is in the function read as array, you can pass different arguments. And your data set still is open. So what we can call band or anyway, so I will just recap once again. So first I will open my data set, ps gdal.open file name. Then we were calling, once we have to fetch the band as well. So from dataset, I have fetched the band 1. Now suppose if in my band I am just interested on only reading in only subset of my entire image, and so if I don't pass any argument to band.read as array, so by default it reads my entire image. Now suppose if I am interested only in reading the partial image, so what I can pass it these arguments like x offset. X offset is from the which pixel number I want to read the image. So instead of 00, I want to read from the pixel number 600, and y offset represents my line number. So now I am interested in reading the image from pixel number 600 and line number 600th pixel. So instead of 00, I am going to, like, if you take this, instead of going to 00, I may be going, I might be reading from this portion onwards. So X offset will tells X offset from where I want to read, and Y offset is my, X offset is my pixel number, Y offset is my line number from where I want to start reading the pixels. Then window X size. Actually, window X size is how many pixels I want to read. So from that, instead of reading all pixels, I just want to read 512 pixels. So similar way, win Y size tells me how many pixels in Y direction. So now what I am doing, I am from pixel number 600 and line number 600, from that onwards, I am just reading 512 pixels in X direction and 500 pixels in Y direction. So if I see data dot shape, it says 512 by 512. So now I am able to successfully read only 512 by 512 pixels. So let us visualize this portion. So now here you can see that instead of entire image, we have just read this particular, this subset of our image. So this way, suppose if you know the coordinates of coordinates of your area of interest, so your coordinate, your area, so your by applying reverse geo transformation, you can calculate from your latitude longitudes to pixel number and line numbers. Once you got the pixel numbers and line numbers, then you can just read your partial data. Then this way you can subset your image. So once this is done, then we can delete, so that it frees all the resources available with your image. Now next thing you will see that how do we read our raster block wise. This was, we have read just a partial image. Now we will see that. So what happens? Rasters are generally made of blocks. So raster could be made of like these blocks. So if we see initially, we have seen that the block size was 1151 cross 1. So what means a block is 1151 pixels in X direction and one pixel in Y direction. So in our image, our block size is like, you can say that one row. So there are 1151 columns we have read. Our original size of our pixel was 1151 cross 1151. But when we queried the block size, so image ultimately is represented in the form of blocks. So the block size of 1151 cross 1. So this is our one block. So rasters are made of blocks. So blocks corresponds to a rectangular sub part of the raster. So like here you can see that these different colors, these are the blocks of our image. So the first value in the width of the block and the second value is the height. So first value, whatever, if you see that 115 block size, so here it was showing the block size of this band one was 1151 cross 1. So this image is stored in the block, so the width and height. So this block is one row, you can say. So then depending on your format, this block size may vary. So knowing the block size is important when efficient reading of a raster data set is needed. So when you want to efficiently read the data, so you need to know the block size. Or suppose if your image is too huge to fit into the memory and you want to read it efficiently, block by block, efficiently, like suppose if you want to do some processing on certain blocks, so then you can read the image block wise. So for now we'll see that how do we read our image block wise. So like we will read first this block, then second block, third block, or any other block. So first thing anyway, similar way, we are first need to open the GDAL. So we are, by opening, we are not reading the contents of our image. We are just establishing a link to our file. So now suppose I am fetching out my band one. Then I'm just querying my width and height of my image. So similar way, now suppose if you want to get the block size. So for block size, you need to call on the band dot get block size. So band dot get block size returns the block size. So it has returned 1151 cross 1151. Now, so what we will do in the loop, we will keep on reading it block by block, block by block. So here what we are doing, for x in range 0 to x size, and we are incrementing in x by block size of x. So first reading one block, then we are incrementing the offset by the number of pixels in our block size in x. Similar way, in y direction also we are going 0 to y size, then we are incrementing it by the block size in y direction. So just we are checking that till x plus block size is less than our size of our image. If it is less than, then we are just number of columns we are incrementing it, and we are just reading it block by block. So similarly, now finally we are reading read like we show in partial array, read as array x y. So x and y offsets from where we have to start this we have calculated here, and how many columns and rows we have to calculate. So this way we can read an image block by block. If I see here data, so this way we can read image. So now we were reading 1151 cross 1. So data dot shape, if I see, it shows 11 cross 1. So this was reading a GeoTIFF image. So anyway, the time is over now. So tomorrow we will continue from. So today we have seen reading a GeoTIFF image. Tomorrow onwards we will see that how do we read HDF format or NetCDF format, or even yesterday a student asked about reading from WMS. So tomorrow we will cover those portions. So thank you for today. Now we will take some break, and if you have any questions, I will take up the question.